Warm hello and warm welcome from us. Thanks to everyone here who is joining us on our talk, where we explain our journey over the last few weeks and months that in the end led to this beautiful board that seems to be very easy, very simple, but we in the next half an hour will explain how we come there and what it actually does beside doing a small noise, blinking a few LEDs, and why it helped us both to communicate better. My name is Stefan Kraus. I'm a senior software engineer, and in my day-to-day job, I mostly take care of the security and the testing of medical applications. And in the project, I was the person who is majorly responsible for Zephyr and the implementation of the application we talk about later. And I'm not alone. No coffee for us. I have Andy with me who will take over.
Yeah, very welcome from my side. I'm Andreas. I'm also a software engineer as Stefan. We worked in the same company before. Now I switched to another one. And in this project, as I mostly find the hot end of the soldering iron, I will play the role of the hardware electrical engineer. And we will take you through the story of a typical embedded project you might have encountered in your career before. So our agenda will be planning, proof of concept, and then why we wanted to make it better. So let's start first. What do you need to develop a product? So at first, you need a problem you want to solve. Or, even better, you invent your own problem your product is your perfect solution for. Let's call it vision. So, our problem was, we were in the office, and imagine a very long hallway with, several offices here and there. And Stefan and me couldn't be much more apart than what we were. And Stefan had a great place being next to the staircase leading to the coffee machine, so I had to walk all the hallway down, asking everyone for coffee, which is quite annoying for both of us. And direct messages on computers, well, you can ignore them. So then your coffee experience is also not that great because nobody would react. Group chats, we all know them. They are annoying as well. So we need another solution. And then we came up with our vision. So we were in the IoT team before, and then it's quite easy to say, hey, we are IoT. Let's build a thing that does the job for us. And we wanted it to be an independent system so that people are not relying on installing software or bringing their own hardware or anything else. And what the thing should do is just broadcast hey, we want to drink coffee all together. And we also wanted to be interrupting, but not too annoying, because when you are streamed into your coding, then we want to have something that interrupts you a little bit, but not too much. So we wrote up some requirements because we are engineers. For our solution, we wanted it to have a very low power consumption because those things would run 24/7, and we don't want to waste energy. We wanted it to be cost efficient because when you distribute it over different offices, then you won't pay too much money, right? And we also wanted to use it mesh networking because corporate IT bringing things into Wi-Fi, and then you get asked questions what these things are doing, who will be supporting it, security patches, and so forth. And we wanted it to have good Zephyr support because, that's what it's all about. So we grabbed what was lying around in our drawers, which would happen to be some Nordic NRF DKs. And we just flashed the Bluetooth mesh sample on it and did a bit of range testing. and we pressed the button 1 on one board, then it was flashing the LED on the other board. And the range testing was not that great that it ranges all the whole way down, but for every other office we got good connection. So problem basically already done. LED blinks, so that's it. Then we will go into the proof of concept phase. So we did our research in our product development before, and now we build our first prototype. We defined our minimum valuable product, which should have one button, one buzzer, some RGB LEDs because they are easy to control, should be USB powered, and have a Bluetooth mesh. So the first prototype was an ESP32 dev kit because they are quite cheap and much available. And I designed a shield to provide our minimum viable product needs, which is one button, the big green one, an RGB strip, and a buzzer. And because I'm embedded software engineer, I also added space for more buttons and a free pin header, just in case I want to use it for something else. Yeah, and the software working on it was based on the Zephyr Bluetooth Mesh sample, which was quite easy to port on this ESP32. And we also use the built-in Zephyr state machine framework to manage all the different states we want to have during the coffee call. And now Stefan will tell you a bit of the software development.
Yeah, thanks, Andreas. I want to talk a bit about our software development process. But process is a very big word because I pretty much knew what Zephyr was already providing and that basically everything is available somewhere if you know what you want to do, what you search for, and then find it properly. So let's, for example, say the state machine. Yeah, we discussed that we want to have a very simple state machine with 3 different states, idle state, call as active state, and a call as announced state. And let's say, okay, I have two different ways to go into it. I could write my state machine myself, or I will look into if it's already provided by Zephyr. Most of the time it's, oh, Zephyr already has a pretty good implementation that is configurable and perfectly usable for my use case, if you know where to search for. So I knew there was a state machine framework which works pretty well. I just need to find out the right kconfig, which is sometimes a bit hard. And then I look into the example or the samples folder, take the code, copy it into my application, change it a bit to match what I actually want to do, make it compile again for the board that we already have, and then I do the exactly same thing with, for example, the button interactions or the LEDs. And therefore that a lot of things are already there, it was very fast to actually bring up the application as it is. So this was done in like half a day, just because it's mostly copy-paste. Unfortunately, that leads to pretty much the following repo structure, which we will discuss later. But the highlights here, or what we keep in mind, therefore that I really just want to use not so much time and just have a working product so I can tell him that I want to drink coffee right now. Everything is in this CoffeeCaller app folder. There's a bit of abstraction for the hardware because Andy did it, not me. A Bluetooth math for the communication and a big main C. And while Andy did not only do the hardware, but also until we waited for the hardware to arrive, the device tree and all the abstractions that we needed later. So after like a week or two, the hardware actually arrived. We flashed it. It worked pretty well, therefore that we only could compile it before. But then we did the rollout into our office. So we used about 15 boards, 1 in each office room. Worked pretty well. But as it is, the colleagues that are sometimes surprised what you did give you feedback. The feedback can be classified into two things. The product issue that we got directly from our colleagues, which are, hey, the buzzer is too loud, so we stick something on it. The colors are not matching. Sometimes the board lose their mesh or do not properly redirect the messages. So we sometimes thought that the mesh is very fragile or even splits up into different ones. So we decided, okay, let's change a few more things. But then several project issues came in. Like, for example, I only tested it in the end on the board. It only compiles for exactly this board that was designed. The abstraction is basically not there. There was the state machine file with like 400 lines of code containing everything. And as a funny side note, when we tried to upgrade the ESP32 to a newer version, the Bluetooth mesh example did not work at all anymore. So we opened up an issue on Expressive, and they were like, well, Bluetooth mesh was never officially supported by us. We just had luck that we tried out a commit where it suddenly worked for one of the boards. So this was, good luck for our prototype, bad luck for the next few weeks that we did then. And especially for Andy, he needed to manually solder everything. And with 20 boards in the first charge, that was not the nicest thing to do. So in this thing, we decided, hey, Andy, come on, we are engineers. Let's just do it properly so it's not only open sourceable, but we are also not ashamed of what we produce in our free time anymore. So Andy, tell us about the professionalism of the hardware.
Yeah, sure. So as we rolled out our first proof of concept, got some customer feedback in, we are now in our third phase of the project, the professionalism. So we decided let's do better because we are still engineers. So we said, let's do our hardware our own. We want a compact PCB because we wanted to have it on the desk of everyone, so it shouldn't take up too much desk space. I didn't want to have any through-hole components because I don't want it to wobble when you press the buttons. We also want a SoC with good Zephyr support because ESP32 wasn't at this point. And we wanted it to be USB-C powered because, micro USB is a bit annoying. And also for the software, we want to support for native SIM because then we can, just compile it without the hardware. I think Moritz also mentioned it in his size talk that they made use very much of this feature of Zephyr. And we don't want to put everything in this application folder because it's easier testable when everything is a lib, such as the communication layer, the application logic, and some hardware-related functions. Also, because we are engineers, we want to automatically test it. And we wanted an officially supported communication mechanism. So, Bluetooth mesh was always a bit tricky. So in your project, when it comes to how to select your components, there are a few things you want to consider. You want good the SoC support. You want a good driver support in Zephyr. So it's better to first look in the Zephyr device tree binding. So which things are supported, and then go to your hardware suppliers and look for things that that match what Zephyr supports. We wanted also some sensors on it because in our office it gets quite warm, so there was a need for a temperature sensor to also build a temperature sensing mesh. You have to think about solder it by hand or manufacture it as a whole thing, and of course the price tag. So what we chose was the NRF 52840 as a SoC because we made some good experiences with it, also in our proof of concept testing with the ranging, and we also decided for a full PCBA manufacturing, so no soldering at night to roll out on the next day, and also the AQFN package, which is like a ball grid SoC, is not very convenient to hand solder at home. And also the production volume is not scalable if you do it all all yourself at home. So let's dive a bit into Agile. Our first iteration. We choose a credit card as a form factor to just start with something. Put a LED strip, RGB strip on it. The button, the buzzer. Also added some free pin headers because I'm a software engineer. I like to have some free pin headers to put something else on it. We also added this quick connector, which is a somewhat standard for extending I2C bus over so to daisy chain I2C bus to add more things you want to play around with, and also for debugging a 10-pin JTAG compatible SWD port. And then, like in every project, you have some feature creep because I thought it's Agile, right? And then you take your creation and show it around to some friends which are also involved in the problem, in the project. And then this guy appears. It's Tobias. He will have another talk later on, so join him. It's also funny most of the time. And he said, that's nice, but I wanted to have it, would be nice to have it in a coffee cup shape. And also for extra buttons and for GPIO controllable LEDs, it would also be nice. So, I mean, you already saw it, pre-production thing. Yeah, I changed the outline of the board, added those 4 LEDs on the right side next to the JTAG port, and 4 buttons to the smaller buttons to the next to the RGB LEDs. And then I thought, hey, that's good. But then there's more Agile. So, LEDs in a straight line are fine, but for my trainings, I would really like to have them in a rectangular shape and not, in that fashion. And also, for servers to connect would also be really nice. And also some NFC connector to test this functionality in trainings. And then, okay, let's add it. And then the board gets quite crowded at that moment. And when you think you're done, then, responding to change over following the plan, because then you show it around, and then what about mounting holes? And then you look at your KiCad design and think, oh, where should I put those mounting holes anymore? But hey, the size is not specified, so I managed to put in four M2-sized mounting holes. And that is then pretty much what the end product looks like. Quite a journey. And every time I thought, hey, I couldn't fit more on this board, I just started to move components around, reroute everything, and then, okay, I have done this. Good. So I've never done really much KiCad before. I just tried and errored everything. In the classical embedded projects, like I did it over years, you're now on the stage like, hey, we have the final hardware. Let's start coding. Between these boards is not only the form factor and some pins routed to different connectors on the SoC, but it's also a complete different CPU architecture. We have the Extensor Tensilica on the left side and the ARM Cortex on the right side. And before Zephyr, you had to tell all your engineers, hey, you have to now install your ARM compatible toolchain, and pretty much rewrite everything because we changed a few pins and also the MCU and stuff like that. But that's where Zephyr really covers you, because the device tree and the subsystem is really what is a game changer for me in embedded development. Because From the board on the left side and the repo structure Stefan showed you and the hardware abstraction layer I put on top of it, they are, it's better called subsystems in Zephyr's naming. We didn't do any changes on it. So I asked Stefan, so hey, did you do anything? Have you done much to it? So because I wasn't sure about how good it's working, and he just said, no, I just copied it over and it just worked. So using your device tree and your subsystems is really, really the key to support your application. Because Zephyr gives you all these basic GPIO functions and stuff like that, but your application developers, they don't really care about toggling a GPIO port, so they want to switch a specific LED on or off. And in this example, it's quite simple. It's just an RGB strip where you say, hey, I want to set this first LED green or red or anything else. And that's what I provided as the hardware software affine engineer to my application developer. And so Stefan, all he was about to know was, just like, hey, I have this RGB strip. I don't have to know anything about hardware. I just can say, I want to switch this RGB strip on or use the button and don't care where the pinning goes, what MCU architecture is under it. And that's the point where Stefan will tell you about how the software development worked.
Thanks, Andy. Yeah, we had the advantage that we already had some experience with Zephyr, and so we already had some best practices in using and properly accessing the device tree. So, for example, we used a lot of aliases, so we have always a buzzer 0, and the exact mapping is then described in the device tree layout. So even I was a bit surprised that it worked so well, but in the end I could just took my application I wrote before, compiled it, and it would work as good as before, where I would say, okay, this is a big point for Azure. That is great, so it still works, but from a software perspective, I'm just not satisfied with the state the project was in. So as we told before, we wanted to improve, especially in the testing and automated testing part, but also just in the structure of the project. And my first goal was that my application, my CoffeeCaller, shall please also be compilable for native sim. So the native simulator is a POSIX Arch-based board, the successor of native POSIX. And the great thing is it allows the application to run on your native Linux without needing to always flash it on the board, test everything on real hardware. As even though Andy also wrote a UF2 bootloader for it, it just takes time and some effort. So when we have it on native sim, we have several advantages. For example, we do not need to flash it anymore. We are not forced to wait until the new hardware version is actually at us from our PCB vendor. And also I can do real tests, executable tests, system tests on the CI without having a hill setup, a hardware setup, because that is possible, but a bit out of scope for our hobby project. So the big issue is things do not suddenly just compile on native sim if you do not take a bit of care about your code and how you think about things. Let's, for example, take the LED strip. Yeah, a native simulator board. This laptop here, unfortunately, does not have an LED strip I can just use. So we need to take care of all the hardware specifics that the board brings, but are not trivially simulated or done. So our goal, and there are different ways to tackle this problem, but we decided there is also the native sim device tree. Let's extend it with the additional features or nodes that we need so our board compiles. And there are two ways or two cases how it works. The first thing is you are lucky and there is already an emulator provided by Zephyr. And you can just take a drop-in replacement for it. For example, for the watchdog that we implemented. Yeah? For our real board, we have the Nordic VDT watchdog. That is the upper right node in the device tree. Yeah, it's compatible to that. And for that, after some searching on the file structure in Zephyr, and it was not so clear and trivial to find, there is a drop-in replacement that you can just use for a native system. For example, the Zephyr counter watchdog. It takes a native POSIX counter as a watchdog timer, and you can just put this node from this type in your device tree, and with the right alias, it will just compile and even work properly. So when we don't feed this watchdog anymore, our application would even stop on this Linux, so I can also simulate some other behavior things. That was the good part. Unfortunately, and especially for things that are not used so often, there are no drop-in emulators available. For example, the LED strip. In the Zephyr 4.1 release, there are like, I think, 6 or 7 different ones. But right now, and we will change that, there is no emulation available. And we decided, okay, we have never done that for Zephyr before. Let's write our own emulation or our own drop-in replacement so we can compile it. I just call it fake LED strip. I will also show you how I implemented it, added some attributes, and just put that in as another node in my overlay. Thing is, Zephyr does not have something that is compatible to it, so I needed to do 2 more things. I need to add a binding first in the DTS bindings folder with the name of my node and how it's compatible. Just drop it in, add a small description. In these drivers, I also have some kind of include, and I just included the default properties that all LED strips shall have. That is a chain length and a color code in which order your RGB colors are. And secondly, and that was a bit more work, at least I thought so, but it's quite simple. You add a C file in the drivers, you tell it in the first line, hey, what's this compatible for? In this fake, it must match the Zephyr fake LED strip one. I implement the device API. Depending on what you want to implement, it's like in this case 2 single functions, which in the end do not need to do a lot of things, but must be there. And I need to define how I create my devices, need to get it some static space, some static storage, and define it what it shall be used. The implementations in our case are doing a bit of logic to really emulate the LED and to also print it, but generally, if you really want to just have it compile, you could just return 0 and fulfill the contract of the driver. And these are, I think, only 60 lines of code, and then this part compiles. And I did that with every device that have no built-in emulation. I think it was only the LED strip and the PVM. And then it made compile and sped up the next steps drastically, as I'm not waiting or reliant on any hardware. So the next thing that was bothering us is that everything else is also in this app source folder. For example, the whole hardware abstraction layer that provides some compatibility functions for us. So we can make this buzzer twice in a short row, or long or short. And the good thing is, as these were already abstracted properly, we just took it, we took all the includes, put it in the include folder in the right structure. We took the source code, extracted it out into the lib folder. We use the lib here as these shall be having not so much state in our own thread, but are just functions to call. And modify the CMake list, the kconfig list accordingly, so we can select or deselect specific features in case we have people that are not wanting to have a buzzer all 5 minutes in their office. Okay. The good thing is, now that I have it abstracted, I can also do proper testing with it. Let's talk our buzzer Aldrin as a short example for that. I have this static buzzer alias node at the top, and the buzzer works that we start and stop timers so we do not block things. And I'm, in this case, not a big fan of unit tests at all, because they look like, okay, have you exactly this call to the timer, this call to the timer? So for this, I used a Z-test integration test and have a real timer. The good thing is, when I have it in native sim, the test gets quite deterministic. And my thing was, okay, let's do some very small and simple tests that it works with the right calls and the timers are properly firing. So for example, when I have it wanted short, I do a call count, I sleep a bit and check that it's off after some time, and this works quite well. Next thing was then, what I personally see as a best practice and what I really like is, in the end, my application shall have no to nearly no code at all, but everything shall be a subsystem, so I can select features that I want and compose my real application from selecting subsystems. For example, I do not only want to have a CoffeeCaller application, but also my temperature subsystem on it. And the first thing that we abstracted was the broadcast subsystem. We switched from BLE Mesh, as it was not so stable as we thought, to an openthread mesh. And in this case, I do not only rewrite the application layer, but I also abstracted it in a subsystem, the broadcast system, which provide a pub/sub service where different other subsystems could subscribe to, send messages to, but also get responses. And here I also thought about something that I think is really important, and that is, how do I also make it work on the native sim emulation? Using a proper emulation for openthread and the chip was quite hard, so I took a shortcut and just, when I compile for native sim, I instead use a local queue and a local socket, so I have no real openthread, but to test the business logic or the sending logic itself, it works quite well. So let's look shortly in the kconfig. Yeah, we see here the distinction between the openthread transport and the local queue transport. I have one kconfig option, so I can select which one I want to use. By default, for native sim, it takes local queue. For everything else, it takes openthread. And when I compile, I use the Zephyr macros to check, okay, which of these symbols is defined right now. And depending on that, I link the one C file or the other C file in. Same with the tests. When I activate my kconfig test flag, I also compile in some helper functions so I can reset and access more variables. And as I said, I want to have nothing. I don't want to have anything in my app folder. I did the exact same thing with the state machine or the CoffeeCaller subsystem. Put in everything from there into an own subsystem. And in the end, the main function of the CoffeeCaller app looked like that. It's an int main, does nothing because I need something to fulfill my CMake build system. But the only kconfig that I really need is, hey, I want to have this subsystem, and all the logic is inside that. Last but not least, what I also like for my subsystems is I want to have a shell so I can interact with it without real hardware, and which also eases my tests. For example, I implemented, or I used the Zephyr shell subsystem and implemented two commands. One that is just I press a button, which pretty much simulates this one, and another call that simulates that a message comes in with who sends the message and do I take part or not. And for each of these, I also had some samples that are just checking that it still compiles, that it still shows what's the minimal set that I need to bring the subsystems up, and also have tests. And the big advantage of the shell subsystem is there is a new shell harness where you just write in shell commands, write in what you expect as an output. And now all the tests that we had for the sport are pretty much, okay, simulate a button press, wait a bit, send this message, wait a bit. Okay, is it a yes or a no? How do you handle if something weird happens? And there's no need to really having hardware in our CI or somewhere, because we can all emulate it on native sim, with a big advantage. Okay. And after some more refactorings, more steps, we come to what we call the lessons learned.
Yeah. So, lessons learned in Zephyr and next steps. it's all there. You just need to know where to look for, and you have to find it. Native sim is very handy, and it's key for fast iterations and testing. And the regulatory part we completely forgot about, because as you can see, my employer would have sponsored some boards and manufactured it because it was designed to have some space on it to place your own company logo on it, manufacture it, and yeah, use it as giveaways at like this event today. But someone mentioned, hey, there is no CE marking on it. We have no EMC, no radio. Yeah, so if you know anyone who is familiar with this process, just hit me up, because yeah, that's at the moment a bit of a blocker for this whole thingy. And then I want to thank you, everyone, especially Tobias, for always being there for us, giving tips, helping us out, not always being the annoying guy in the corners, making comments on what we did. You can find the project on GitHub. There's the KiCad file, also with the production files available, so you can just download it and yeah, put it into manufacturing. And also the whole Zephyr CoffeeCaller code application is on another GitHub repository. Yeah, and with the UF2 bootloader, I forgot to put a link on it. It's easy to program also in big batches. So thank you very much. We have, I think, a few minutes left for maybe 3 or 4 questions. Thank you.
Nobody has questions?
Oh,
there he is.
Perfect.
Did you add or think about adding, like, you know, the system now basically as it's based on thread, border router, and now you can have a nice web interface?
Yeah, we thought about that. The question was if we thought about adding a border router to our openthread network. And yeah, that was basically the idea to switching to openthread, because in our in my old company, in his still company, we were also separated across different floors, and it was quite, yeah, not that the mesh range wasn't that good to go over different floors. So the idea really was using openthread and the border router protocol to distribute the calls across different floors. We haven't tested it yet, but from my understanding, it should be possible to just distribute it, or also collect the temperature data, put it up in the cloud, and then visualize the heat map of our building. Yeah. Yeah, the price tag, because putting just a plain SoC on the module. So the board, as you see it here, if you manufacture it like in a batch of 200, then the price per board is with shipping and all around like €9. And the module itself is starting at 15 euros, I would say. But yeah, those modules have their CE mark on it, so you also pay for that. That's one thing I just forgot about. Yeah, but that's the reason I put this plain SoC on it. And also I just wanted to get familiar with more hardware design, because in my day-to-day job I am also the interface between the electrical engineers and the software developers. So for me, it's important to understand some certain things of hardware to help them debug, not only software but their product, right? I think there was one more question. No? Okay. Yeah. 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 So the question basically was like how Zephyr compares to the classical RTOS development, which is established in companies. As Moritz said from the Zeiss company yesterday in his talk, they also switched from classic RTOS. Could really recommend his talk here, which pretty much answers this question. But for us, or for my perception, it also was like I did ThreadX a lot before, and my last customer project was they had different MCUs from the same distributor, from the same manufacturer, but yeah, you have to do a lot of CMake magic and if-defs to get the whole thing from having one application and one board and just combining them, and also switching between your prototype version. That's what I wanted to show with this slide over here. Switching from your prototype version to your final product. With Zephyr, this step is just made easy. You can start with off-the-shelf development kits you can buy from. Start your application, business logic, product level stuff, and then when you are finished with designing your hardware, you basically just have to write your device tree, fix here and there some kconfig options, and then you can switch to it. But yeah, the learning curve and switch over from classical RTOS development to Zephyr, I think it will take some time in big companies to really see the value of it. Yeah. But my perception is that Zephyr gives you all these things for free. You just have to learn it once, and it's also for new employees very easy because you only have you can learn what's open and not what's proprietary for this company. So when you personally switch to another company, you can just continue what you have done before. Okay, we are now 1 minute over time. Thank you for your questions. I think we will be at the Zephyr booth at some point. We will have some of these CoffeeCaller boards. So if you want to play around with it, just come to us. Yeah, thank you.
Thanks.